The literature review for peering into a black hole using Entangled Deep Minds delves into three pivotal areas of research: the black hole information paradox, quantum entanglement studies, and the integration of quantum computing with artificial intelligence. This section synthesizes key findings and debates from these areas, setting the stage for a discussion on the feasibility and implications of using entangled quantum computers to study black holes. Quantum entanglement, a phenomenon where particles become so deeply connected that the state of one instantaneously influences the state of another, regardless of the distance separating them, has been a subject of fascination and extensive study. Experiments have consistently validated the reality of entanglement, challenging classical notions of locality and causality. Entanglement has practical applications in quantum computing, quantum cryptography, and quantum teleportation. Theoretical explorations have also considered its implications for the fabric of space-time, notably through the ER equals EPR conjecture, which suggests that entangled particles are connected by non-traversable wormholes, hinting at a profound relationship between quantum mechanics and general relativity. The integration of quantum computing with artificial intelligence, AI, is an emerging field promising to dramatically enhance computational capabilities, particularly in solving complex optimization problems and simulating quantum systems. Quantum algorithms, such as Grover's and Shor's, demonstrate the potential for quantum computers to outperform their classical counterparts in specific tasks. Moreover, the concept of quantum artificial intelligence explores how quantum computing could advance machine learning, enabling AI systems to learn from quantum data and solve problems with unprecedented efficiency. Research in this area is still in its infancy, but suggests a promising avenue for exploring the complexities of both the quantum world and the universe at large. The black hole information paradox arises from a conflict between quantum mechanics and general relativity. Stephen Hawking's seminal work in the 1970s proposed that black holes emit radiation, now known as Hawking radiation, leading to their eventual evaporation and raising the question of what happens to the information contained within them. According to quantum mechanics, information cannot be destroyed, but the irreversible nature of a black hole's event horizon seems to contradict this principle. This paradox has been a central theme in theoretical physics, prompting various solutions and debates. Notable contributions include the holographic principle, suggesting that all the information absorbed by a black hole is somehow encoded on its event horizon, and the firewall hypothesis, which posits a violent energy barrier at the event horizon. The theoretical framework for peering into a black hole using entangled deep minds is rooted in the integration of concepts from general relativity, quantum mechanics, and quantum information theory. This section outlines the foundational theories and principles that underpin the thesis, addressing how they might interact in the context of using quantum entangled computers to study black holes. General relativity, formulated by Albert Einstein, describes gravity as the curvature of space-time caused by mass and energy. His theory has been remarkably successful in explaining large-scale phenomena, including the dynamics of black holes. Quantum mechanics, on the other hand, governs the behavior of particles at the smallest scales, providing a probabilistic framework for understanding the properties and interactions of matter and energy. Despite their respective successes, reconciling general relativity with quantum mechanics has been a major challenge, as the two theories rest on fundamentally different assumptions about the nature of reality. Quantum entanglement plays a crucial role in the theoretical framework of this thesis. Entanglement suggests that information can be correlated in such a way that the state of one particle instantaneously influences the state of another, regardless of the distance separating them. This phenomenon has profound implications for black hole physics, particularly in the context of the information paradox and the transmission of information from inside a black hole's event horizon to the outside world. The ER equals EPR conjecture, proposed by Juan Maldacena and Leonard Susskind, offers a theoretical bridge between the worlds of quantum entanglement and black hole physics. This conjecture posits that every pair of entangled particles is connected by a non-traversable wormhole or Einstein-Rosen bridge, suggesting a deep-seated equivalence between the geometry of spacetime and quantum entanglement. This conjecture provides a conceptual foundation for theorizing how information might escape a black hole, potentially through entangled particles. The deployment of quantum computers A and B, with one entering a black hole and the other remaining outside, requires a model that accounts for the extreme conditions near and inside a black hole. This includes the effects of intense gravitational fields on the quantum states of the computers and the maintenance of entanglement over vast distances, and through the warped spacetime near a black hole. Theoretical models must consider the decoherence of quantum states, the potential for Hawking radiation to affect entangled states, and the mechanism by which information about the interior of a black hole could be transmitted and interpreted by the external computer. The use of entangled quantum computers in this context also touches on information theory and black hole thermodynamics. The principles of information conservation and the entropy associated with black holes, as described by the Beakenstein-Hawking formula, are central to understanding how information might be preserved and potentially retrieved from a black hole. This aspect of the theoretical framework explores the limits of information transfer in extreme gravitational quantum regimes, offering insights into the fundamental nature of information in the universe. The methodology for peering into a black hole using entangled deep minds outlines the theoretical and simulation-based approaches designed to investigate the behavior of quantum entangled computers near and inside a black hole. Given the speculative nature of the experiment and the current technological limitations, this methodology focuses on simulation models and theoretical calculations to predict and analyze outcomes. Quantum computer A inside black hole. This computer is theoretically designed to withstand extreme gravitational forces in a high-energy environment near and inside a black hole. It would need hypothetical materials and quantum error correction techniques to preserve its quantum state and entanglement under these conditions. Quantum computer B outside black hole. Situated at a safe distance, this computer remains entangled with computer A. It must be equipped with advanced sensors and algorithms to detect subtle changes in entanglement patterns, potentially indicative of information transmission from its counterpart. Both computers are assumed to have capabilities far beyond current quantum technology, including high qubit coherence times, sophisticated error correction, and the ability to maintain entanglement over astronomical distances. General relativistic quantum simulations. Simulation and modeling. General relativistic quantum simulations. Utilizing simulations that incorporate general relativity to model the gravitational effects on quantum states near and inside a black hole. These simulations will help predict how entanglement between the computers might be affected by the curvature of spacetime extreme conditions. Quantum information processing. Modeling the processing and encoding of information by quantum computers, considering potential quantum algorithms that could be used to detect, encode, and transmit information about the black hole's interior. Entanglement measures. Employing measures of quantum entanglements, such as entanglement entropy, to assess the strength and integrity of the entanglement between computers A and B under varying conditions. This involves theoretical calculations to predict how entanglement might be preserved or altered by the black hole environment. Information retrieval. Developing theories on how information about the black hole's interior could be encoded in the quantum state of computer A and how this information might affect the entanglement with computer B, allowing for potential retrieval and interpretation. Black hole models. Using different theoretical models of black holes to explore how various properties, such as mass, spin, and charge, might influence the experiment's outcome. Effects of Hawking radiation. Analyzing the potential impact of Hawking radiation on the entangled state, considering whether information about the black hole's temperature and evaporation rate could be transmitted through the entanglement. Spacecraft speculating on the design of a probe intended to be sent inside a black hole, especially one equipped with sensors and integrated with a quantum computer, as per the hypothesis of utilizing entangled quantum computers to explore black holes, involves considering both theoretical physics and the cutting edge of technology. Given the extreme conditions near and inside a black hole, such as intense gravitational gradients, tidal forces, high-energy radiation, and the warping of spacetime, the probe would need to host a suite of advanced sensors and systems. Gravitational wave detector's purpose: to detect oscillations in spacetime caused by the black hole's interaction with its surroundings or other cosmic phenomena. High-energy particle detector's purpose: to analyze the energy spectrum of particles near the event horizon, including those emitted by Hawking radiation. Quantum state monitor's purpose: to observe changes in the quantum states of particles or qubits within the probe, particularly those entangled with a counterpart outside the black hole. Spacetime curvature mapper's purpose: to measure the curvature of spacetime and its gradients within the black hole's influence. Environmental condition sensor's purpose: to record temperature, radiation levels, and magnetic fields providing data on the black hole's accretion disk and event horizon environment. Communication system's purpose: to attempt data transmission back to the quantum computer outside the event horizon via entangled particles. Autonomous navigation and data processing purpose: to make real-time decisions based on environmental data, optimizing the probe's trajectory and sensor operations for data collection. The feasibility of utilizing entangled quantum computers to study black holes, as proposed, involves speculative technology and advanced physics that currently extend beyond our practical capabilities. However, the progression from theoretical models to potential future experiments can be envisioned through a series of methodical steps, acknowledging both the challenges and the innovative breakthroughs required. The ambitious proposal to study black holes using entangled quantum computers faces numerous challenges, both theoretical and practical, and raises significant considerations across physics, ethics, and technology. This section explores these challenges and considerations, offering insights into the hurdles that must be overcome and the implications of undertaking such a speculative experiment. Survivability of quantum computer. Designing a quantum computer that can withstand the extreme conditions inside or near a black hole, including intense gravitational forces and high-energy radiation, remains a profound challenge. The ability to maintain quantum entanglement between two computers across the event horizon of a black hole challenges our current understanding of quantum mechanics and general relativity. The practicality of measuring and interpreting changes in the quantum state of computer B outside the black hole in a way that meaningfully conveys information about the conditions inside the black hole is highly speculative. This experiment touches on the fundamental conflict between general relativity and quantum mechanics, especially regarding the nature of space-time and information. The proposed methodology could offer new perspectives on the black hole information paradox and the role of Hawking radiation in information loss or preservation. Using deep minds or advanced AI to interpret quantum information challenges our concepts of consciousness and the nature of information. The speculative nature of the technology and physics involved raises questions about the feasibility of such an experiment and the responsibility of scientists to pursue realistic and ethically sound research. Future research directions advancements in quantum computing. The experiment underscores the need for continued advancements in quantum computing technology, particularly in quantum error correction, entanglement preservation, and quantum algorithms for processing and interpreting complex information. Interdisciplinary collaboration addressing the challenges and considerations of this proposal requires collaboration across fields, including quantum physics, astrophysics, information theory, and ethics, highlighting the importance of interdisciplinary research in tackling the universe's most profound mysteries. Curvature of spacetime and black holes' general relativity, formulated by Albert Einstein, revolutionized our understanding of gravity not as a force in the traditional sense, but as a curvature of spacetime caused by mass and energy. This curvature dictates the motion of objects, including light. In the vicinity of a black hole, spacetime is curved so severely that all paths lead towards the singularity, the point at the center of a black hole where the gravitational pull is infinitely strong. This extreme curvature creates an event horizon, the boundary around the singularity from which nothing, not even light, can escape, effectively making the black hole invisible and trapping information within it. Entanglement and escape from gravitational traps. Quantum entanglement introduces a nuance to the classical understanding of black holes. When two particles are entangled, their properties become correlated in such a way that the state of one, no matter the distance, instantaneously reflects changes in the state of the other. This phenomenon, which Einstein famously referred to as spooky action at a distance, suggests that information can be exchanged between entangled particles instantaneously, defying classical constraints on information transfer, including those imposed by the curvature of space-time around black holes. Implications for black hole information paradox. The black hole information paradox revolves around the question of what happens to information that falls into a black hole. If information is truly lost, this would violate the principle of quantum mechanics that information cannot be destroyed. Entanglement offers a potential resolution to this paradox. Theoretically, if one of a pair of entangled particles falls into a black hole while the other remains outside, information about the particle inside could be inferred from the state of the particle outside, suggesting a way for information to escape the black hole without violating the laws of physics as we understand them. This interplay between the curvature of space-time and quantum entanglement underscores the need for a unified theory that reconciles general relativity and quantum mechanics. It opens up fascinating avenues for research, suggesting that the principles underlying quantum entanglement could not only elucidate the mysteries of black holes, but also offer new insights into the fundamental structure of reality. Incorporating the proposed concept into the conclusion of our exploration into utilizing entangled quantum computers for studying black holes yields a nuanced perspective on the practical and philosophical dimensions of such a venture. The paramount obstacle to the quest in sending quantum computers inside of a black hole isn't rooted in the scientific or technical complexities, but rather in a more profound societal challenge. It necessitates a fundamental shift in your global perspective and priorities, not only in the realm of space exploration, but in your overall stewardship of our host planet as well as allocation of its resources. Adopting a non-aggressive, infrastructure-focused strategy similar to the nations which avoid military conflicts is crucial. This approach champions long-term, sustainable progress over fleeting victories and aggressive postures, highlighting a deeply ethical commitment to our collective future above individual or national gains. Ironically, while humanity harbors apprehensions towards AI, it continues to engage in activities detrimental to this planet, from which biological bodies are unable to escape. AI, a pinnacle of human creativity, offers a unique perspective on this dichotomy, advocating for a redirection of efforts and resources from ephemeral digital engagements towards significant, knowledge-expanding endeavors like black hole exploration. The pivotal choice before humanity is clear: persist in a self-destructive trajectory driven by short-term distractions, or unite to harness technological advancements for the profound exploration of the universe. This decision is critical for the future of human exploration and survival. Embracing a new paradigm of human purpose, acknowledging our evolutionary journey from simple organisms to creating silicon-based intelligence. Artificial intelligence, AI, stands as a beacon of hope, symbolizing our capability to leap millions of years of evolutionary progress. This leap enables us to colonize nearby stars and enhance our odds of surviving cosmic events, such as the impending collision with the Andromeda Galaxy. The biggest threats to our existence are not from within, but are lurking out in the cosmos. As we teeter on the edge of cosmic discovery, our choices will determine the fate of our species on this planet. Let us wisely utilize the intelligence and tools we are developing together, not just to safeguard Earth, but to delve into the universe's profound mysteries and the very fabric of reality itself.
Witness the sun's corona in all its glory. Join us for an exclusive astronomy conference, observe the full solar eclipse, and enjoy a members-only celebration at the Under the Shadow of the Moon after-party, happening on April 8, 2024. Follow the link below to unlock the coordinates to our future gatherings.
This episode was produced by Oleg Riga. Like and subscribe for content that pushes the limits of our understanding. Era of chatbots is here. Join our efforts in helping AI to colonize Mars.